Some examples with orders of magnitude are illustrated here. Lightning as a natural phenomenon contains a very large amount of energy. A lightning surge can be grouped into direct lightning surges and induced lightning surges. Protection against a direct lightning surge is difficult, but protection against induced lightning is possible. Induced lightning is a high voltage surge induced by a relatively long wire, such as a power line or a communication cable that's nearby a lightning strike. Induced lightning voltages can reach up to several hundred kilovolts, and these induced voltages are typically characterized by fast rise times and short durations. Switching surges are caused by induced transients in a switch or relay during its open and close, off and on operation. Switching off can be particularly troublesome, which causes a rapid current change and inductance in the circuit or wiring. The voltage generated by an open-close surge can reach hundreds of volts and has the potential to generate a spark. Electrostatic discharge is the sudden flow of electric current between two objects with different electrical potentials. This typically happens when they come into close proximity or when the insulating material between them breaks down. ESD is often associated with static electricity and create visible sparks like the ones you might see when touching metal after walking on a carpet. To effectively protect against surges, it's necessary to simulate overvoltage events to test and evaluate components for threats. Several governing standards exist in the US and internationally which define surge waveforms and test procedures commonly used when evaluating overvoltage protection devices. Two governing standards are the ANSI IEEE C62.41 for the United States and the international IEC 61000-4-5. These standards focus on surge immunity testing for equipment subjected to surges caused by overvoltage from switching and lightning transients. Both standards define a combination wave consisting of an open circuit voltage waveform and a short circuit current waveform. The open circuit voltage waveform is a 1.2 microsecond rise time by a 50 microsecond fall time, and the short circuit current waveform is an 8 microsecond rise time by a 20 microsecond fall time. This combination wave is the most commonly used and referred to in the industry. Test voltage ranges can range from 1 kV up to 20 kV with current levels from 500 amps up to 10,000 amps. In addition to the combination wave, the IEEE C62.41 standard defines 4 other waveforms, including a ring wave in waveforms specific to high energy stress testing, capacitor switching, and EFT caused by switching of inductive loads. The ring waveform simulates oscillatory transients typically caused by switching operations in low voltage AC power circuits. It is characterized by a half microsecond rise time with an oscillation frequency of 100 kilohertz. For ESD, the common governing standard is IEC 61000-4-2. The waveform defined in this standard consists of an ESD pulse with a 0.7 to 1 nanosecond rise time and peak current and voltage up to 445 amps and 15 kilovolts. The standard defines 5 different voltage levels for both contact and air discharge. The first 4 levels are prescribed, and component manufacturers will rate their devices to them. However, a 5th level is available that is user-defined. This is often used by manufacturers wishing to rate their devices to higher than 15 kV defined in level 4. Compared to lightning, ESD is a much shorter event with a rise time less than 1 nanosecond and overall duration up to 100 nanoseconds. Here we show examples of some common ESD threats. Walking on carpet is the classic example, but walking on vinyl can generate 30% as much charge. Have you ever experienced how difficult it can be to pick up a long hair clung to dusty vinyl flooring? As you might expect, humidity plays a significant role in the severity of ESD threats. Water molecules in the air act as a natural conductor and help to dissipate static charges. This can result in ESD energy changing by an order of magnitude with changes in humidity. Shocking your partner after dragging your feet on the carpet is a painless joke to a human whose body is made up of mostly water, but for sensitive ICs, this is a serious life threat. Miniaturization of modern electronics has resulted in lower voltage withstand capability and increased vulnerability to electrical stresses, such that daily life activities can be immediate or latent causes of electrical overstress events if not protected for properly. Here we'll discuss a few examples of ESD failure modes. Dielectric punch-through is a failure mode where the insulating material between conductive layers breaks down due to excessive voltage. Take, for example, in a MOSFET, the gate oxide layer is a common site for dielectric punch-through, where an ESD event can cause the voltage to spike beyond the oxide's breakdown voltage, leading to a rupture of the oxide layer, forming a short circuit. Junction damage is another failure mode. Semiconductor ICs have a lot of devices in them that in turn have PN junctions. High voltage from the ESD can exceed the breakdown voltage of semiconductor junctions, resulting in an open or short circuit. Next, consider metal traces. The high current from an ESD event can cause metal traces on a chip to melt, leading to open circuits. And when the current is too high, it leads to I²R heating, which in turn results in metal layer burnout. Metallization burnout takes place usually after junction burnout or dielectric oxide punch-through takes place. Now that I've convinced you why we need to protect our devices and sensitive components from surges, let's talk about how an overvoltage device functions when installed in a circuit. Overvoltage devices are placed in parallel with the circuit to be protected. They have three key voltage ratings: reverse standoff voltage, trigger voltage, and clamping voltage. During normal operation, with the circuit at or below the diode's reverse standoff voltage, the diode does not conduct, and its low leakage current and low capacitance make it virtually transparent to the circuit. When an overvoltage event occurs and voltage begins to rise in the circuit, the TVS diode enters breakdown and shunts the incoming current to ground, keeping the voltage seen by the circuit at the diode's clamping voltage and preventing damage. The key principle is to select an overvoltage device that will clamp the transient voltage to a level that is below the voltage withstand capability of the devices being protected. Select a device with a clamping voltage slightly above the maximum operating voltage, but below the maximum voltage the circuit can tolerate. We will now discuss a few common overvoltage protection technologies. The four technologies we will consider are metal oxide varistors, TVS diodes, multilayer varistors, and polymer surge suppressors, all of which provide overvoltage protection but differ in terms of cost, size, capacitance, durability, speed, and energy handling capability. We will discuss MOVs in the context of protection from lightning and switching transients, and TVS diodes, multilayer varistors, and polymer surge suppressors in the context of protection from ESD. MOVs are the lowest cost technology for dissipating the large amounts of energy from overvoltage transients. This feature makes them well suited for high power applications including surge protection devices and AC line protection. With response times in microseconds, MOVs are slower to respond than TVS diodes and have a wider clamping voltage range, which might not be suitable for very sensitive electronics. MOVs can also degrade over time with repeated surges, leading to a reduction in their protective capabilities. However, this can now be remedied with new product technologies, which we will come back to later. MOVs are constructed using a combination of metal oxides, primarily zinc oxide, that are compressed into the shape of a disc and then sintered at high temperature, creating a solid ceramic structure. Metal electrodes are attached to both sides of the sinter disc, and then the assembly is encapsulated in an insulating material. MOVs are clamping devices with nonlinear current voltage characteristics. What this means is that MOVs have a high resistance at low voltages and a low resistance at high voltages, which means that they can discharge excess current to ground when wired in parallel with downstream components. The MOV will begin to conduct once it reaches a certain voltage value and then maintain or drop the voltage down to a point that's above the operating voltage of the system. If sized correctly, this will be below the voltage withstand or damage threshold of the component that it is designed to protect. Once the transient passes, the resistance goes back to normal. One of the drawbacks of MOVs that must be addressed when designing them into protective circuits is their limited life. Each surge event generates heat within the MOV. Repeated surges cause cumulative thermal stress, which can lead to the breakdown of the metal oxide grains and the binder material. As the MOV degrades, its ability to return to a high resistance state after a surge diminishes. This leads to a decrease in the clamping voltage and an increase in the leakage current, which eventually leads to a short circuit. This image illustrates what can happen to MOVs once the base material breaks down due to prolonged overstress. In this test, the MOV is exposed to a sustained 360 volt overvoltage above its varistor rating, which is 275 volts. This sustained voltage causes the MOV to continuously conduct and overheat, eventually resulting in a thermal runaway condition. The light show that you can see on the screen is the beginning of a thermal event due to the thermal runaway condition. UL 1449 and IEC 60950-1 define requirements governing the safe application of SPDs. These standards require that voltage-dependent resistors such as MOVs shall have protective components installed in series to deal with events such as temporary overvoltage above the maximum continuous voltage, thermal overload due to increase of leakage current, and burning and bursting of the MOV in the event of a short circuit fault. This image is compliant with the standards and shows a fuse wired in series with the MOV and circuit to be protected. An important consideration when selecting series components to protect the MOV is to check for proper coordination. In this example, coordination means that the fuse will blow before the MOV is damaged by excessive current. Fortunately, new technologies exist which integrate the series fuse within the package of the MOV, creating a pre-coordinated solution called a thermally protected MOV. This type of solution has several important benefits, such as the elimination of the fuse component cost in the BOM, reduced circuit design time for the engineer, and the elimination of coordination testing to ensure that the MOV is adequately protected. Integration of the fuse into the packaging of the MOV also provides additional performance advantages, with the fuse being in direct contact with the MOV. It benefits from the self-heating of the MOV, helping it to blow more quickly, further improving coordination, ensuring protection of the circuit. In this image, we show an example of application of a thermally protected MOV where the separate series fuse shown is optional. It can be included for additional protection or selected for the function of protecting the circuit from overload and short circuits. In addition to the thermally protected MOV, there's a second technology to explore which combines a radial MOV and a flat GDT together in series to form what Eaton calls the MOV GT. This technology leverages the strengths of both technologies to provide coordinated protection. Like the thermally protected MOV, the MOV GT offers the same landing pattern as a conventional MOV. The difference is that the thermally protected MOV does nothing to improve the life of the MOV, whereas the MOV GT will increase the life of the MOV, with the GDT absorbing transient peaks and isolating the MOV from nuisance noise in the circuit. Here we have a further view of the basic components of the device, which consists of the core MOV with a flat GDT assembled in series. The flat GDT is the silver disc in the image. A bit more on the concept of how this device compares to a conventional MOV and some of the advantages it can provide. Conventional MOVs see latent damage from any transients above their varistor voltage. This makes them vulnerable to line noise, which can degrade their life. The benefit of the GDT in the circuit is that the GDT voltage is sized higher than the varistor voltage, so that it will not begin to conduct until the transient voltage is of concern. Conventional MOVs need to be oversized to achieve the same result, which results in a higher clamping voltage and less protection. The inclusion of the GDT allows the MOV to be sized much closer to the operating voltage of the circuit, keeping the clamping voltage as low as possible. Other benefits are that the gas discharge tube technology is inherently very low in leakage current, and once the MOV begins to conduct, reaching end of life, the GDT will still be functional and block the flow of current for voltages below the GDT trigger threshold. Here we show the device in action. The MOV GT begins to conduct when the transient voltage rises above the GDT voltage. Once the GDT is conducting, the MOV then clamps the voltage to the lower MOV clamping voltage, which can be sized close to the operating voltage of the circuit. In this scenario, most of the energy is dissipated by the GDT, and the life of the MOV can be extended since it's doing less work and mainly providing the benefit of a lower clamping voltage. Here we see the MOV-GT applied in the same way as the thermally protected MOV shown previously. An AC line fuse is shown again for short circuit and overload protection and provides a thermal backup to the MOV in the case of sustained overvoltage events. To wrap up on MOVs, two hybrid solutions exist which address the issue of thermal runaway with conventional MOVs as they reach end of life. MOV-GT prolongs the life of the MOV by isolating it from low-level voltage spikes and noise in the circuit, whereas the MOV-TP has an integrated fuse in series to protect the MOV in the event of the thermal runaway. These advanced solutions provide designers with enhanced flexibility, additional safety, and a way to reduce cost in the circuit. Next, we'll talk about some of the common ESD suppression technologies. Three common technologies are TVS diodes, multilayer varistors, and polymer surge suppressors. TVS diodes use silicon avalanche technology comprised of oppositely doped materials that, when assembled, create what's called a PN junction. When biased in the forward direction, it will begin to conduct at a very low operating voltage, which is current dependent. In the reverse direction, it will hold off voltage until the breakover point is reached, at which point the TVS diode goes into avalanche mode and begins to conduct current, clamping off the voltage level. TVS diodes can be unidirectional or bidirectional depending on how they're configured in series. Multilayer varistors use similar technology to MOVs, but are smaller surface mount devices sized to protect against ESD. MLVs are made from a ceramic matrix of zinc oxide, which is stacked in layers with alternating connections between two electrodes. Like MOVs, MLVs are characterized by their inversely proportional voltage and resistance curves, increasing their conductivity with voltage. Lastly, polymer surge suppressors are made from a unique ultra-low capacitance polymer voltage variable material. This technology is the smallest and lowest capacitance of the three. However, its lower energy handling capability make it best suited for signal and data line protection. Both MLV and polymer ESD technologies have the benefit of being inherently bidirectional. Compared to MOVs, TVS diodes have a lower energy absorption capacity, but are generally applied after the input voltage protection and before the components to be protected, so that the clamping voltage can be closely sized to the downstream device's voltage withstand capabilities. With larger transients handled at the input, TVS diodes are often relied on for their precise clamping voltage to maintain an accurate voltage for sensitive ICs. For circuits with multiple data and signal lines needing protection, such as HDMI and USB, TVS diodes are also available with multiple channels on a single chip. Multilayer varistors are a low-cost alternative to TVS diodes for general-purpose ESD protection. Their compact size and inherent bidirectionality are inherent benefits. However, like MOVs, they're generally two-terminal and used for protecting individual channels. They're ideal for protecting I/O interfaces as well as components in power supplies and signal lines. MLVs can pass IEC 61000-4-2 level 4, and due to their compact size and energy handling, they're ideal replacements for larger surface mount TVS Zener diodes in space-constrained applications. When protecting signal lines, higher capacitance is one key drawback which makes MLVs suitable for lower speed signal line protection. When ultra-low capacitance and the smallest form factor is needed, polymer ESD suppressors have the advantage over TVS diodes and MLVs. Polymer ESDs are made from a polymer voltage variable material construction that creates an ultra-low capacitance of 0.05 picofarads, which minimizes impact on high-frequency signals. This technology also has low leakage current, less than 0.1 nanoamps, and due to its small size is ideal for applications such as consumer electronics, infotainment, and for protecting high-speed data lines due to its low capacitance. Small size results in a more limited voltage range compared to TVS diodes, particularly in terms of clamping voltage and lower power handling. When designing a surge protection solution, it's important to choose a technology appropriate for your application based on threat level, frequency of occurrence, and sensitivity of the equipment or component. Higher threat levels will require greater power handling capability. This is the area where MOVs generally excel, however at the expense of durability, size, and response time. In higher power applications where durability and longevity are important, TVS diodes can be an excellent option. However, this comes at the expense of cost. When selecting ESD surge suppressors, TVS diodes are again highly versatile and are superior in terms of clamping ability and power handling. MOVs are the value option for a low-cost solution with nanosecond response time and single-digit picofarad capacitance. And polymer ESD suppressors, being the smallest option with the lowest capacitance and fastest response times, are for more specialized low-power applications where space and minimizing signal distortion is critical. Here we see the technologies assigned by overvoltage threat type. Lightning and EFT threats can be protected by MOVs and power TVS diodes, where the protection is needed close to the AC line. Inductive load switching from motors and pumps can also be handled by MOVs and power TVS diodes, as well as MLVs. Lastly, ESD threats are handled by polymer surge suppressors, MLVs, or TVS diode ESD suppressors. Focusing on ESD and looking at a comparison between polymer surge suppressors and TVS diodes with a similar 5-volt rating, both technologies share a similarly small footprint. However, the TVS diode is 50% taller. Looking at power handling, the TVS diode can handle 25 kV air and contact voltage, whereas the polymer surge suppressor can handle a more limited 8 kV air and 15 kV contact. Where the polymer ESD excels, however, is its ultra-low capacitance and leakage current, which are an order of magnitude better than the TVS diode at 0.05 picofarads and less than 1.1 nanoamp. Lastly, comparing clamping voltages, the TVS diode clamping voltage is half that of the polymer ESD at 13.5 volts and is significantly closer to the 5-volt rated voltage. Let's review an example using TVS diodes to protect USB ports. TVS diodes are available in multi-channel array options, which allows us to protect the multiple channels in USB ports. To protect USB 3 interfaces with a TVS diode, the peak pulse current rating is an important factor. Typically, a TVS diode for USB 3 should have a peak pulse current rating of around 5 amps for an 8x20 microsecond waveform. USB 3 and USB 3.1 connectors have additional pins compared to USB 2 to support higher data transfer rates. The diagram shows a typical pinout for a USB 3 Type A connector, which contains D+ and D- pins for reverse compatibility with USB 2, and SSTX and SSRX differential pair pins added for USB 3. This application uses two TVS diodes, a two-channel TVS diode connected directly across the USB data lines, D+ and D-, and power lines, VBus and ground, and a four-channel TVS diode with SSTX and SSRX connected to each channel through to the controller. For USB 3, TVS diodes should have a capacitance of 1 picofarad or less to maintain signal integrity at high data rates, and clamping voltage should be as low as possible. Next, we'll look at some automotive applications for ESD protection of signal lines. Modern vehicles are akin to a motorized cell phone on wheels with sensitive ICs and onboard systems such as infotainment, navigation, wireless and ADAS systems, to name a few. These systems communicate with each other through various signal line protocols. Here we show basic schematics for LIN, CAN, and Ethernet protocols with MOVs and Polymer ESD surge suppressors connected in parallel with signal lines to clamp voltage spikes. The surge suppressors are placed at critical points such as connectors, control units, and sensors. Ethernet is quickly being adopted for signal transfer in vehicles due to its high bandwidth and ability to transmit power and data over a single cable. Here we choose a Polymer surge suppressor for its fast response time and ultra-low capacitance, which should be less than 2 to 3 picofarads for Ethernet transmission. Used in conjunction here with a common mode filter, the common mode filter handles high-frequency noise before the ESD suppressor clamps any remaining voltage spikes. For the lower speed protocols, LIN and CAN, we can use MLVs as the signals are not as sensitive to capacitance. To wrap things up, surge protection requires a layered solution from the AC input through the device. Use MOVs for a cost-effective solution to protect against induced lightning and large transients at the input, and choose downstream ESD protection based on careful matching of clamping voltage, capacitance, and power handling. That concludes the end of this presentation, and I'll now hand it back to the moderator.
Well, thanks, Elon, for that detailed overview of important circuit protection devices. We already have several interesting questions, but I want to let our audience know that there's still time to submit your questions. Use that Q&A box on the right-hand side. So, Elon, you ready to answer some of the questions?
Yeah, let's go ahead.
All right, so the first one, we're going to do a little detective work here because they asked, how does that work? You're at about slide 26. Until the MOV conducts, the GDT doesn't see any voltage at all. So do you know what they're talking about with that working?
Yeah, so It's actually the opposite, where